This is an introduction to causal inference, aka causality, and we'll go first through what the problem this field is trying to solve, and then we'll go through some tools and solutions for it. So this topic in itself, on its own, it's a whole discipline. There's full courses on it. It's both part as the econometrics field, so which is part of. It's about quantifying economic phenomena, as well as the data science portfolio, which is where I'm at, right? And the first concept to understand is that correlation is not causation. We all have a very natural inclination to find patterns that explain the things that we observe. And for a very good reason, right? It's all about understanding. So once you have that grasp of the underlying mechanisms that explain something, you know, you do this and this happens, then you can leverage that to make things better, right? So we have the very natural tendency to create those associations. So for example, we can observe the following. Excuse me. Since everyone's starting eating more ice cream, the sunburn has gone up. And you observe this every summer, and you might start to be tempted to say, hey, I think the ice cream is causing sunburn, right? Another example, the babies named Ava correlate strongly with the housing price index. So the more babies named Ava we had since 91 until 2009, as it goes up, the housing pricing has gone up. And interestingly enough, the babies named Ava drops, and the US housing bubble happens, right? So are the babies named Ava caused the housing bubble, right? And a third example is a very strong correlation we can observe here between the number of mozzarella cheese consumed and the engineering degrees, the civil engineering degrees awards given. So we might be very tempted to do the correlation that, you know, if you want more civil engineers, you get more people eating mozzarella, right? So these are very tempting correlations to do, but correlation is not causation, right? These connections between events that we observe, they can either be true, false, or the third tricky one is that they are false, but they are correlated, and it's very easy to get fooled by. So I'll give an example of all of these. So correlations which are true, causalities are true. So excess calories will lead to weight gain. There's a direct correlation between those. It's just physics. If you eat more than you spend in number of calories, you're going to gain weight, right? False examples of will be Avas, of course, did not cause the housing crash, right? And mozzarella is not leading to more civil engineers. These are just coincidence. And there's this whole other subtopic, which is how to lie with statistics, right? And it's an interesting thing on itself. And there's one of the points there is that if you look hard enough, you can find always something that will explain whatever you want. That you can always find correlations if you look hard enough through data in different examples. Because coincidence can actually happen. It's actually expected them to happen. So that's why correlation is not causation. And then there's this third bucket, or this third way, which are the tricky ones. I call the tricky ones, or more nuanced ones. And those are easy to get fooled by. For example, alcohol is highly correlated with death. So you might be tempted to say alcohol kills, right? And out of those examples I'm giving, I think everyone might have more pause on this one. It's like, right? It's like there's a strong correlation. So alcohol kills, but not necessarily, right? So alcohol is basically a manifestation of the same underlying root problem, right? So, for example, the people who drink less alcohol might, in general, just be eating healthier and taking better care of themselves, doing more exercise, while the folks with a heavy consumption of alcohol, they kind of might not be having the same type of care with their body, and so they are also the ones who end up dying earlier, right? So it's just a manifestation of both. But again, like you see, it's a little bit trickier one to say. So for example, the example we saw before, which is the ice creams and correlated with sunburn. So again, it's one of those false but nuanced events too. Although this is a good example because we can see, of course, it's nonsense. The ice cream is not causing sunburn. Again, the ice cream, the way you can think about it is that ice cream are a manifestation of the same root cause, which is in this case the hot weather. So the hot weather is leading to folks to end up buying more ice cream, and it's also the thing that it's causing the sunburn. And here I can introduce a new concept which is very used in this field, which is the confounding factor. And in this case, the sun is the confounding factor. It's kind of this third factor that kind of makes us confused or tricky, but it's actually the underlying cause of things. So why, in changing gears now a little bit, but why is all this relevant to know about, and why does this matter? So there's actually a lot of value in the understanding and quantifying causality also in the business context, right? So for example, did a product change lead to increase retention, engagement, or sales? Like imagine you release a new feature on the product. Like, is that leading to more engagement, retention? How do you prove it? Bug fix, does it actually truly reduces crashes? A marketing campaign or even a growth initiative, is it leading to increased users in sales? How do you prove that correlation, right? So again, this is one of those examples. If we truly understand the underlying mechanism, there's a lot of value to it. So let me walk through an example of the problem of correlation is not causation, that I've seen very, very often happen in a business context. So it's the following. So let's first consider here on the right this chart that has these four different panels, and we just think of users and split them in the following way. So we can think of them as of splitting users as early adopters and users with high engagement, right? If you split the users in that dimension, which is a very common thing for business, you will end up with these four quadrants, which is the ones who are early adopters and have high engagement, they are fans. And then on the other extreme opposite, you will see the ones who are late adopters and have low engagement. Those might be like the users who don't even know there's a new version, right? And they might be thinking they use the app very sparsely, etc. So with that in mind, we can now walk through an example of that I see happening many times, that we can fall into the trap of correlation as not causation. So now imagine you have a product. You release a new feature in the product, right? And then you are interested in knowing, did your feature lead to better retention over time, right? That's the goal. So you go and select all the folks who have used your feature on one hand, right? And then you go and select the users who have not used that feature on the other hand. And then you go and compare 1 month later, you're going to compare those two. Which of those groups had the more retention 1 month after, right? And you find that the ones who used your feature had a lot more retention. So you declare the feature launch as a success, right? You say, yay, right? This is successful. My feature is awesome. But not so fast, right? So if we go a little bit one step deeper, what might be happening here? So let's go back to the part where we select users. So when you select users that use your feature, you most often will be selecting fans naturally, because those are the ones which are early adopters. They see the feature coming up more. Those are also the users who are using your product a lot more because they have high engagement, right? So they might be the users all the time using it, and they see something new popping up, they try it out, right? So that is one of the cohorts you're comparing. The other one is the folks who rarely use it. So they might not even come to the client. They might not know there's a new feature. So those were the ones who are anyway, independently if the feature is there or not, they're going to be the ones who will have less retention. So what you're doing here is comparing apples to oranges, right? You're not really comparing apples to apples. And this is a very, very common situation that happens. And again, this would be a nuanced one, right? Because we see a strong correlation with usage of the feature and strong retention long term. But this is, again, one of those problems where there's no causality, and it's a very nuanced one that it's easy to fall into the trap. So how do we solve this? What are the techniques that we can help to solve those things? So the first one is, and really the gold standard, the thing that we should always use when we can, is what it's called the randomized controlled trials. And I'll explain it through an example. Imagine you have a new drug. So in the medical context, you imagine you have a new drug and you want to try if it's really efficient or not, right? So you go and find all the folks who are sick and and agree to do the trial. You split them into two groups. To one group you give the drug, to the other group you give a placebo. So you don't really give the drug, and then you see a month later, if the folks who got the drug got better or not versus the ones who didn't. So that's like the basis intuition in how the mechanism of how the randomized control works. And you should do that always when you can. By the way, I have published a video and a tool which you can actually use. I call the A/B test check calculator. So you can use that whenever you run A/B tests to check if your treatment, if the thing you are testing out, it has a significant statistical difference or not. So I can leave a link to that. Now, there are many cases where A/B test is not possible. They, in general, are expensive. You can imagine that, for example, in this medical trial, to rounding up all the folks who might be sick, having them to go through the test, having the time to wait to see the results, and etc., go through all of that is a complicated one. In the digital world, it's way cheaper to do those A/B tests, but of course not for free. It still takes some effort, and it takes time too. So being able to infer causation from observational data has value. And observational data is just data you already collect in a normal basis, and it could be data in the past even. So imagine you can just have some methods where you can go look at all the data you have already collected, and you can start telling, oh, this thing made a huge difference that happened at some point, right? So there is some value to the methods which are even outside of the randomized controlled trials, and I'm calling them these quasi experiments. So they are methods that try to do a kind of infer causation also, even if you don't do a true experiment or randomized controlled trials. But do note, warning or FYI, that these quasi-experimental methods, they have to be done in a very thoughtful way, because they can be a lot of traps along the way. I do recommend to have a dedicated data scientist for this, like as you will see in some of the next examples. Okay, so let me go through the first one we have here. Matching methods, and I'll go through just a couple. Matching methods. So the main concept here is trying to remember I'll bring in the example we talked about before, and the idea is actually to do apples to apples comparison. There's a collection of methods that can do this, but I will try to just communicate the intuition, the base intuition of this method, and then the other details can be seen later. So I'll bring in this example we talked about before, which is comparing apples to oranges. And the whole idea of this method is trying to compare apples to apples. So let me go through an example of how we would do the earlier example by leveraging the idea of matching methods. So maybe the folks who use the new feature are the users that have the most engagement to start with, right? That's what the premise we started with before. They're just the ones who are more engaged anyway. So a better apples to apples comparison is actually to first select all the users that have high engagement. We just look at the high engagement, we forget everyone else, and then we're going to split them into two groups. The group that have used the feature versus the group who did not have the feature, right? So then we are comparing high engagement, that use feature, high engagement that did not use the feature. So almost like comparing fans versus fans. And this would be a more fair way to do it. It would be a closer apples to apples comparison, right? So we are not comparing fans anymore to the ones that are not, they don't even know there's a new version, right? We get close. And the whole concept of this matching method is exactly try to get closer of matching apples to apples. For example, in that medical trial test, imagine you have the groups that you're gonna give the drug and the one you don't give. Like if you put 20-year-old in the group that you give the drug and you put 90-year-old in the group that you don't give the drug, right? See how this is unfair, right? Because the ones who are 20 years old, they will most likely recover even if you give them the drug or not, right? So the matching method's intuition is that you actually try to compare apples to apples. So you would use 20-year-olds, give the drug, and you compare to a 20-year-old that you don't give the drug. So that's the basic intuition. I hope it makes sense. Now, the other one I'll talk about is about the propensity score matching. So, and I'll use the same example of early adopters and high engagement. So, in the previous example, I said that the main hypothesis that the users who end up using the feature are the ones that have the highest engagement, right? But how can we be sure that's what it is? Is it high engagement the only thing making him try the new feature? So now imagine that I tell you this. Imagine that this product actually we have gamers and we have suits, which I'm calling suits as just not gamers in business context, right? And turns out this feature is mainly for gamers. So if we would just use, in the previous comparison, if we just pick up users that were high engagement, and then compare them with the ones also with high engagement that did not use the feature, we might end up comparing gamers versus suits. And we know these typically have very different types of patterns of behavior and retention long term. So again, it would not be, we would fall into the trap of not comparing through apples to apples comparison. So what this propensity score matching does, it's a more, I would say, scientific method of looking at all the behaviors of all the users that use your, that end up using the feature, and then it will tell you what exact profile are those. So the method might tell us, oh, actually were the gamers, the high engagement gamers, which were using that feature. So you should actually select the cohort of high engagement gamers, and then see which of those use the feature versus the ones who did not. See, so it's kind of a step even further within that apples to apples comparison and getting closer and closer. So the propensity score matching is very similar, I would say, to the matching idea, but it's a kind of a scientific way of doing it a little bit more precisely. So, and the way it works on the background is that it actually creates a model of what is the exact profile of the users who are using your feature. So you just create a machine learning model. You say the goal is to predict who is going to use the feature, and then you put all the types of behaviors, and then the model will tell you of the users more likely to use the feature. It will tell you, oh, these are the important weights in that model, which is high engagement and gamers in this case. So see how this, so it's a way of, like you see in the picture, it's a way of matching and organizing and putting apples to apples comparison a little bit closer, so you get closer to a true comparison. And see how we are, progressively getting closer to that apples to apples comparison. And this is one of the problems, or the tricky bits of these quasi methods, is that sometimes you have to be very careful. You might not be missing something big that you haven't thought about. That could be actually the confounding effect behind it. But yeah, that's the intuition of these two methods. It's a field with a lot of investigation and with a lot of other methods. So I talked here about randomized control trials, matching and weighting. waiting, there is this difference in differences, which I might also do a video on. There is double machine learning, which is one of very recent methods. It's actually from 2018, if I'm not mistaken. So it's a very interesting development, leveraging a lot of machine learning algorithms, etc. Doubly robust learners, meta learners, instrumental variables, which comes from econometrics. Some of them, meta learners, are pretty cool. So there's more of this to explore and to be aware of. I wanted mostly to give an intuition, and the main things to take away is that correlation is not causation. So be very careful of our tendency to do those associations. Naturally, we kind of have that tendency, especially that bucket of the tricky ones, the nuanced ones. And that the way to solve it is having this intuition of trying to get closer of apples to apples comparison. And also, I will leave here a quick reference if someone is interested, which are the popular libraries that are done in Python that are used for this. And I know these three get a lot of usage. EconML, DoY by Microsoft, actually, and Causal ML published by Uber. And they have, if you go and investigate those libraries, they have great stories about how the companies actually use them to understand this causality. A lot of interesting things around that. Yes, so that is it. I hope this is useful. Thank you.